and Transport Research Institute. And today I'm going to talk about one of my newly finished projects. It's about solution for faster development of forest roads in Sweden. So today I will walk you through our work on developing Swedish forest roads aimed to improve the bearing capacity, durability, and sustainability. We will review 5 construction methods and watch short demonstration videos and discuss the key results and their future implication. We will allocate the last maybe 10-15 minutes for questions and answers. So let us start from, can you see the next slide?
I can still see the first one.
Let's move from presentation stage to it's a little bit slowly because there is embedded videos. Can you see now the second slide?
No, the first one.
No. Now?
Yep.
Yeah.
Yes.
Okay, good. So the challenge we are facing is clear. Sweden's long forest road network is vital for our economy. It is under increasing pressure. Timber trucks are becoming heavier, rising from 64 to 74 tons. While climate change brings more freeze-thaw cycles and extreme rainfall. Many forest roads were built according to older design practices and can no longer meet modern demands. The result is higher maintenance cost, reduced transport efficiency, and serious accessibility problems during critical periods, especially during fall and spring seasons. So the aim of this project was to identify solutions that are scalable, quick to implement, and resource efficient. Instead of treating surface problems like potholes, we focused on strengthening the fundamental structure of forest roads from design and construction to operation and maintenance. This project is one of the forest industry's largest recent investments. And our goal was to explore how forest roads can be built smarter, stronger, and more sustainable. So this 3 years project was coordinated by VTI and carried out together with 11 partners from Sweden. Key participants included the Forest Research Institute of Sweden, Kopparforsskogar, Stora Enso, SCA, Sveaskog, Holmen, the Swedish Forest Agency, the Swedish Transport Administration, Riskförbundet Enskilda Vägar, and Södra Funding came from the forest industry with other actors and Vinnova through the Infra Sweden program. So today's agenda, 5 of major forestry company participated in the project. Each built the test road where different stabilization measurements were applied. So we have the Stora Enso built with geocells, type of on-confinement system aid to improve the soil stability. With the SCA, we worked on an improved road crown design to optimize geometry and enhance surface water runoff, while Holmen tested the stabilizing additives, a new one called enzymes. These are environmentally friendly and make chemical improvement to the soil. Sveaskog Holmen focused on testing increased compactive effort. where the compaction effort was enhanced to improve density in the road base. Finally, with copper push, we implemented the stone matrices, which provide both drainage and stabilization in wet and challenging terrains. We will dedicate about 5 to 10 minutes to discuss each method. But before that, I would like to talk about the assessment that we used and adopt to assess the conditions of the developed road sections and the reference sections. One of our key tools was the lightweight deflectometer test. This is a very simple test, as you see in the photo. It applies impact load on the road surface and measures the resulting deflection. And there is an embedded equation on the instrument that will measure the deflection modulus from the measured deflections. And this deflection modulus is a measure of the bearing capacity. Higher modulus means higher bearing capacity. The second measurements is the profile measurements. We also performed this profile measurement using the laser leveling, as you see in the photo, to capture the cross-sectional shape of the road, crown height, side slope, road depth, and surface irregularities. Repeating this measurement over time helps us monitor how traffic and the climate affects the road geometry. The third assessment method is the cheapest one, and we use the visual inspection. By walking or driving the road, we recorded signs of surface damage, drainage problems, structural weakness, potholes, corrugation, lost material, or uneven areas. We also examined ditches and side slopes closely. To evaluate this method, we decided to carry out cost-benefit analysis as the construction cost per increase in bearing capacity. So this analysis was mainly based on data from lightweight deflectometer test because we could quantify the data from lightweight deflectometer test in terms of EVG, the deformation modulus. So let's move forward and talk about the first method. As you see in the photo, Stora Enso implemented geocells, a highly efficient technology, providing strong lateral confinement. These three-dimensional cells or honeycomb structures lock the granular material in place, preventing sidewise movement and greatly increase the stiffness of the roadway. They are especially useful on weak subgrades such as fine grain soil or, as you see here in the photo, waterlogged terrains. I'll show you now a short video demonstrating the illustration of these geocells. Let's go ahead. This is the first section we tested, the geocells filled with the crushed stones. In this project with the Stora Enso, we tested 3 structures, 1 reference and 2 reinforced with geocells. This is the second section, reinforced with geocells. It's filled with existing material. This is the reference one without geocell. So we carried out all the measurements directly after the construction, and the second round was after exposing the 3 test sections to traffic and climate influence. Geocells are proven to be the most cost-effective solution tested. Here I'll give you details information about the results. The geocells improved the load bearing capacity by 52 to 64% compared with the reference section, and made it possible to build a stable gravel road over waterlogged terrain. The 52% gain in EPD was for the section filled with the gravel, pure gravel, and the one with 64 is the one filled with the existing material on site. So overall, they delivered the highest increase in bearing capacity, these two sections, per construction cost unit, and were the strongest performed in the project. Let's move to the second method, which is the improved road crown design, stated by SCA. This method focused on optimizing the road's cross slope to ensure efficient surface water runoff. We tested several configurations to identify the slope that maximize drainage while maintaining safe and stable driving conditions. So we tested the ground slope of 10%, 5%, and left the reference one flat without any slope, just for comparison. So here you can see a brief video showing the design and maintenance process. Let's go ahead. I think picnic during construction is a good idea. This is the first section with 10% crown slope. This is the second section with 5% crown slope. This is the third section, the flat one with zero cross slope. I would like you to focus on this, the longitudinal cracks. This is the first time maybe you see longitudinal cracks in a gravel road. Look here. In the middle. This is the lightweight deflectometer test. Usually the first three drops just to set up the instrument, and the next three drops considered to define the AVD modulus. So let's talk about the results. The results confirm the importance of this fundamental road engineering principles. Sections with properly maintained or improved ground perform significantly better. The 10% and 5% slope sections outperform the flat one, which quickly developed cracks and irregularities. We identified the 4 to 5 crown slope as the optimal choice, even better than the one with 10% slope. The one with 10% slope was uncomfortable for cars. The lightweight deflectometer testing could not reflect the performance of these sections, while here the visual inspection captured the performance clearly. SCA plans to use these findings to encourage contractors to avoid the flat slopes and adopt at least 4 to 5 cross-section slope. So this is all about SCI project, and let's move to Holman project. Holman tested environmentally friendly enzymes additives that chemically modify soil behavior, particularly in clay and silt. Enzymes are biocatalysts that increase the rate of chemical reaction without undergoing any change themselves. So this chemical reaction in the soil surface results in increase the density of soil and thus less water retained. So let me show you a short video about the construction process. Here we tested the 3 sections. One stabilized with the Tirazine from USA. The other one stabilized with a mix fraud stabilizer and dust blocker. We imported them from Finland, but originally they are from Canada. The third section is left unstabilized. There are certain requirements on the materials to be tested. It should be of high fine contents, clay particles, and the plasticity index should be between 5 to 15%. Here, for the first time globally, we used an advanced drone to capture the profiles. We used also the road surface tester to have an idea about the texture and other measurements. So let us talk about the results. The enzyme treated sections showed an improvement in bearing capacity. The section stabilized with the tyrosine achieved about 11% increase in deformation modulus, while the one stabilized with a mix of rod stabilizer and dust blocker achieved about 17% increase in bearing capacity, but required transporting large volumes, which significantly increased the cost because the dust blocker is not an enzyme, but it's a surface sealing material to control the dust. And the expert from Finland decided to mix it with the road stabilizer to get a better result. This was correct. We measured higher result, higher bearing capacity, but this come with an increase in cost. On the other hand, this section with the road stabilizer and dust blocker reduced the dust levels for several months, as we be informed the project leader from home. Of course, this is good for health and safety, but these benefits were not included in the cost-benefit analysis that we carried out, but of course it should be considered in the future. Now we moved on to the fourth method that we adopted in our project, increased compaction. This method focused on increasing the compaction effort, and it was tested by both Sveaskog and Holmen using different types of compactors on different materials. The goal was the same, to deliver more energy into the road material and achieve higher final density. As you know, a denser material should lead to a stronger and stiffer road with reduced water permeability. We applied this approach on both clay-rich soil with Holmen and sandy material with Sveaskog to understand in which condition the higher compaction can result in improved road performance. Before moving on to the results, I'll show you a short video about the construction process. We tried this method with the Sveaskog on a newly constructed road and on an existing road. So we tested 4 sections, 2 newly constructed, 1 reference and 1 with higher compaction, and the same for the existing road. 1 left uncompacted, and the other one is compacted by 8 passes. So regarding the results showed a clear pattern. Increased compaction was highly effective on clay-rich soil, ranking third in our cost-benefit analysis. However, on sandy material, the one tested with this VS Cook, heavier compaction provided no improvement compared to the reference sections. Thus, the added cost is only justified for cohesive, salty, clayey materials. Now we are reaching the final construction method, the last one. It's called the French matrices or the stone matrices. This method implemented by Copperfush Skoger. We tested the use of stone matrices. These are structures of clean coarse stones, typically wrapped in geotextile, as you see in the photo, and buried beneath the road. These structures stabilize the base layer and create internal drainage channels, preventing mixing between the road structure and wet subgrade while allowing water to escape from one bank to the other. So here a short video showing the construction of the stone matrices. Let's see. The geotextile should overlap, should be tight. The geotexture should be topped with a layer of fine fractions. In all these 5 projects, when we noticed that the traffic was not enough, so we simulated the traffic. This is one of them. And then we carried out the same measurement immediately after the construction. And after experiencing the roads to traffic simulation and the climate effects. So I'll move to the results to save time for discussion. So we observed an increase in the road bearing capacity. And this was directly related to how and where the matrices were placed. On test section 1 with distance of 40 meters between the stone matrices, the bearing capacity increased by about 12% compared with the reference section without stone matrices. On section 3, where the distance between the stone matrices was about 25 meters, the bearing capacity increased by 23% in the drain section as compared to the inner drain 1. So this is all about our 5 methods adopted. So let us quickly summarize the critical findings across all these 5 methods. The 5 methods showed positive results. 4 methods boosting load bearing capacity by 10 to over 60%. Of course, the geocells were the clear game changer. The increased compaction method is a specific investment. Of course, higher compaction provide a strong benefit, but only on cohesive clay soil, not on sandy soil. And finally, drainage is non-negotiable. Both stone matrices and proper crown design are absolutely critical components for ensuring our roads can stand up to climate change. Based on these observations, we have some recommendations. The main thing is do not just pick a method, implement the right technology based on detailed assessment of the subgrade soil. Use geocells in waterlogged terrains and the heavier compaction for fine-grained soil. Integrate water management. This is key for climate resilience. Make sure that you choose stone matrices and optimal road crown design in all terrains with the drainage problem, and these terrains exposed to rainfall and thaw cycles problem. You have to look at the big picture, adopt a mentality that the higher initial cost of an innovative technology like geocells or maybe heavier compaction is fully justified by the massive reduction you will see in long-term maintenance. We have published up to now 3 articles, one related to the drone technology for measuring profiles, the other one related to stone matrices, and the third one related to the enzyme stabilization. Also, we have a website of the project. Here you can scan the QR code. This will lead you to the website, and in the website you will see full reports in Swedish, but of course you can translate it by any AI tools. You will see publications like a report of 170 pages. And also we have a YouTube channel, and you can see the full YouTube video in English as well as in Swedish. So this is all about the project. Thank you for joining us today. And I hope this will help us together to build sustainable forest roads. And I'm happy now to answer your questions.
Thanks, Dina. So I will now end recording.